In this section, we are going to look at some theorems that involve chords and the angles formed when they intersect inside a circle. We're going to look at what happens when you draw a triangle or a quadrilateral so that all of the corners touch a circle. And we're going to look at some theorems about tangents. So we've talked a little bit about inscribed angles, the angles where the vertex is on the circle. And we talked about how if you had an inscribed angle, something like this, if that angle was 20 degrees, then the arc measure would be 40 degrees. We've talked about central angles, where the vertex is at the center of the circle. And if that's 80 degrees, then the arc measure is 80 degrees. But sometimes you get angles that are neither central nor inscribed. And that happens when you have two chords, the segments that have endpoints on a circle, and they cross inside a circle and they form a set of four angles in here. And what happens is we are interested in the angle measures of these four angles, angle 1, 2, 3, and 4. And of course, angles 1 and 3 are vertical angles, so they will have the same measure. And angle 2 and 4 are vertical measures, so they'll have the same measure. And we're also interested in the measures of the arcs. So arc AB and arc DC. Now you can tell just by looking at it, the arc AB is a smaller amount of the circle than arc DC. So arc AB will have a smaller measure than arc DC. And similarly here, arc BC is a smaller portion of the circle than arc AD. So arc BC is going to have a smaller measure than arc AD. And that's fine because these are not central angles, so their measures aren't going to be equal to these arc measures. So we want to know, how are the measures of these angles in the middle equal to these arcs? So it turns out that the measures of angles 1 and 3 here are equal to the average of arcs AB and arcs CD, their measures. So think of this as kind of like an hourglass shape, sort of. If you have an hourglass shape here, if you add together the measure of arc AB and the measure of arc CD, and then you divide that by 2 or multiply it by 1/2, so you've added together the two arc measures and you've divided by 2 or multiplied by 1/2, that will give you these two angle measures. And adding something together and dividing by 2 or adding together and multiplying by 1/2, that's how you find an average. So these two angles are the average of the two arcs. Now similarly, if you want to find the measures of angle 2 and angle 4, look at the hourglass shape that encloses those. And you can see that if you add together the measure of arc BC and the measure of arc AD, and you divide that sum by 2 or multiply by 1/2, you will get those two angles. So let's go ahead and look at some examples. So this first one, we want the value of x. So I always like to make sure that that angle that I'm looking for is part of the hourglass shape with the two arcs. So I have the 116, I have the 110, and the x is inside. If you trace the two arcs and then draw the x connecting, that x is inside that shape. So I'm good. Those are the two arcs I'm looking at. So to get x, what I'm going to do is I'm going to take the two arc measures, 116 plus 110. I'm going to add them together and I'm going to divide by 2. You can write it like that, or you can write 1/2 times 116 plus 110. Those mean the same thing. Doesn't matter which way you write it. I prefer to write it as adding together and dividing by 2. So 116 plus 110 is 226. Divide by 2. That's going to give you 113 degrees. So both of these angles in the middle here have a measure of 113 degrees. So you can see 113, well, that's exactly halfway between 110 and 116. If you think of a number line, sorry about that, I forgot to turn the chime off on my email. What's exactly halfway between 110 and 116? Well, 113 is exactly in the middle. That's what it means to find an average, and that's what we've got here. 113 is right in the middle, and that's how this works. Now this one's a little bit different, because if you look at these two arcs, here's the arc and here's the arc. So if we draw our little hourglass shape, we have a problem because x isn't inside my hourglass. If I take the average of those, I'm not going to be finding x. I would be finding one of these angles inside here. But that's okay, because these two angles right there add up to a straight line. If you look at it, they make a straight line, so they have to add to 180 degrees. So I can go ahead and figure out what y is first, and then just subtract from 180 and figure out x. So y is going to be 80 plus 40 divided by 2, which is 120 divided by 2, which is 60 degrees. Sorry. So if y is 60 degrees here, and these two add to 180, well, x is just going to be 180 minus 60. So 180 minus 60 is 120 degrees. And by the way, it's just a coincidence that it's totally coincidence that that's what I divided by 2 here. That will not always be the case, so don't think that there's some cosmic shortcut there. So sometimes you have to do 2 steps. Make sure that the angle you're trying to find is the one kind of inside your little hourglass shape, or whatever you want to call it, bow tie. You can think of it as a bow tie. Kind of looks like a bow tie right there. So make sure that the angle you're trying to find is the one inside the bow tie. You got to find the one inside the bow tie first. If you're trying to find the one outside the bow tie, Find the one inside first and then subtract from 180. All right, now these we're kind of going backwards. So remember what I said here about a number line. Think about on this one, what if I didn't know the 110? And I knew the inside number and I knew the other angle and I was trying to get the 110. Well, just look for a minute at what's going on. To get from 116 to 113 by adding or subtracting, I would subtract 3 degrees. And to get from 113 to 110, I would subtract 3 degrees again. Okay, let's look at the one we just did. Let's look at what y was. Y was 60 degrees. To get from 80 to 60, by adding or subtracting, I would subtract 20 degrees. And to get from 60 to 40, I would subtract 20 degrees again. So when you have an average here, this is what happens. So if I have something like this, I'm told that this arc is 75 degrees and the two middle angles are 50 degrees. And I want to figure out what the other angle is, or the other arc is. So I want to think about, by adding or subtracting, how do I get from 75 to 50? Well, 75 minus 50 is 25. So that means 75 minus 25 is 50. Well, that means if I have to subtract 25 to get from here to here, I also need to subtract 25 to get from here to here. So let's subtract 25 again. What's 50 minus 25? Well, that's going to give me 25 degrees. Now there is another way of doing this, but it is way harder. The other way of doing this is set up an equation. And that is to say, okay, well, if I add the two arcs together, x plus 75, and I divide by 2, I get 50. And then you have to solve the equation for x. Well, you can do that. It works, but it takes so much more time. First, you have to multiply both sides by 2 to cancel that out. And you get x plus 75 equals 100. And then you have to subtract 75. And that gives you x equals 25. Why? It takes so much more time. I would never bother doing that. It's just, it takes a ton more time. So this one, I would look at and go, well, what do you have to add or subtract to get from 114 to 122? Okay, well, that's 8. All right, so I would need to add 8. So to get from 122 to x, add 8. 122 plus 8 is 130. That is so much easier than solving an equation. You can solve the equation if you want to. Go for it. But why? All right. That is theorem number 1. The next theorem involves inscribed polygons. So an inscribed polygon is a polygon like a triangle or a quadrilateral or a pentagon or hexagon. So it's a polygon that's inside the circle and all of the corners, the vertices, touch the circle. So an inscribed triangle looks like this. It's a triangle inside a circle and all the corners of the triangle are on the circle. An inscribed quadrilateral, quadrilaterals have 4 sides and all 4 of the corners are on the circle. So there's a theorem about inscribed quadrilaterals, and it says if you have an inscribed quadrilateral, then its opposite angles are supplementary. The ones across from each other add to 180 degrees. So angle E and angle G add to 180, and angle D and angle F add to 180. So they're not congruent, they're not the same, they're supplementary. They add to 180 degrees. And this is only if all 4 corners are on the circle. So this makes it really easy to do a problem. You look at the ones across from each other and you say, okay, well, those add to 180. So x is 180 minus 70, which is 110 degrees. Y is 180 minus 113 degrees, which is 67 degrees. Please make sure that you write x equals and y equals so that I know which angle is which. Otherwise, I don't know whether you know which one is 110 and which one is 67. So make sure you label them as x equals and y equals. All right, here we go on this one. These two add to 180. So x is 180 degrees minus 77 degrees, which is 103 degrees. And y is 180 degrees minus 60 degrees, which is 120 degrees. On this one, x is 180 degrees minus 81 degrees, which is 99 degrees. And y is 180 degrees minus 90 degrees. Right angle right there would be 90 degrees. So that would be 90 degrees. So that's inscribed quadrilaterals. The next theorem is about inscribed triangles. So this has to do with right triangles in a circle. So it says that if you've got a triangle inscribed in a circle and it is a right triangle, so here's your right angle right here, then the hypotenuse is the diameter of the circle. And the opposite is also true. If you have a triangle inscribed in a circle, and you know that one of the sides is a diameter, then you know it has to be a right triangle. So if you know that one side is a diameter, it has to be a right triangle, and the diameter is the hypotenuse. So the angle across from the diameter has to be a right angle. So let's look at some examples here. So anytime you have a point like this, with that P marked in the middle, that means that that P is the center of the circle, which means that this side right here is a diameter because it crosses through the center of the circle. So because you've got a triangle and one side is a diameter, that means that this has to be a right triangle, and that diameter has to be the hypotenuse of a right triangle. So if that's the hypotenuse, the angle across from the hypotenuse has to be a right angle. Which means that x is 90 degrees. Make that so you can read it. Okay, well, it's a right triangle. We know the angles in a triangle add up to 180 degrees. And if that one's 90, 180 minus 90 is 90. The other two angles have to add up to 90. Because that's always true in a right triangle. The right angle's 90 and the other two angles add to 90. So y is going to equal 90 degrees minus 52 degrees, which is 38 degrees. All right, here's a really skinny triangle, and that makes it kind of hard to see where the right angle is. But if you look at this, that's the hypotenuse. So the angle across from the hypotenuse, right there, is the right angle. So x is 90 degrees. It's not always going to be x, but it was on this one. Okay, the other two angles add to 90 degrees. So y is 90 degrees minus 80 degrees, which is 10 degrees. All right, this one's a little bit different. We can still find y pretty easy. This is the hypotenuse. So the angle across from that, which is y this time, is the right angle. So this time y is 90 degrees. Now we want x. We know that these two angles add to 90 degrees. We want to know what x is, so okay, let's write an equation. X plus 2x equals 90 degrees. So x plus 2x is 3x equals 90. Divide by 3. That gives you that x is 30 degrees. And if you wanted 2x 2x would be 2 times 30 degrees, which is 60 degrees. It didn't ask me for that, but I have a triangle that looks like this. Okay, so we've talked about chords that intersect in a circle and make two angles in the middle. We've talked about inscribed quadrilaterals. We've talked about inscribed triangles. The last thing we're going to talk about is tangents. So remember that a tangent is a line that touches a circle at exactly one point. And that point is called the point of tangency. So a theorem about tangents is that if you draw a tangent and you draw a radius from the center to the point of tangency, that radius will be perpendicular to the tangent. So the radius and the tangent will make a right angle with each other. And the reverse is also true. If you see a line that makes a right angle with a radius, that means that that line is tangent to the circle. That means that this point right here will be the only place where that line touches the circle. It won't barely touch the circle in two places. It'll be the only place where that touches the circle. So since we're talking about right angles, we're going to be looking at some triangles. And we're going to be using Pythagorean theorem. So these say, find the length of the missing segment. Assume that segments which appear to be tangent to the circle are tangent to the circle. So if I look at this, it sure looks like that segment, the 14.4, it sure looks like that is tangent to the circle. It sure looks like if I kept going, it would only touch there once. So it looks like that's a tangent. And this is a radius. So my theorem says that a tangent and a radius will make a right angle. So here's a right angle right here. So I have a right triangle, and I'm trying to find this side over here, which is right across from the right angle. So this is the hypotenuse. So I can use the Pythagorean theorem here. These are the legs, that's the hypotenuse. Leg squared plus leg squared equals hypotenuse squared. I'm just going to call this X instead of question mark. So I'm going to go ahead and pull up a calculator. So 14.4 squared is 207.36. 13 squared is 169. If we add those, we get 376.36. And we take a square root of both sides. And that gives me 19.4. So all you're doing on these problems is using the Pythagorean theorem. But there may be a couple twists that you need to think about. For instance, I have what appears to be a tangent segment out here. The question mark looks like it's a tangent segment. If I continued that on, that would look like a tangent. And here is a radius, so that would be a right angle right there. But I know the hypotenuse is 5, but this 2 is only the length from here to here. That's not the whole side of the triangle. In order to use Pythagorean theorem, I need the whole side of the triangle. Well, it's a circle, and that's a radius. And if that radius is 2, this radius is also 2. Which means that this side is 4. So sometimes you have to do a little thinking to figure out how long the whole side is. So if I look at this, I have leg squared plus leg squared equals hypotenuse squared. So if I call that question mark x, I have x squared plus 4 squared equals 5 squared. So that's x squared plus 16 equals 25. Subtract 16 from both sides, and you get x squared equals 9. Take a square root, and you get that x is 3. So you may have to do a little bit of extra thinking to figure out how long the whole side is. Here's another example. Now what I want here, I don't want the entire side. I just want this piece. But if I use Pythagorean theorem, my right angle would be right here. The 16 would be the tangent segment and the 12 is the radius. Well, that means that this whole thing is the hypotenuse. The thing is, the Pythagorean theorem is not going to give me the question mark. The Pythagorean theorem will give me the hypotenuse. So I am going to call the hypotenuse y. So let's go ahead and get y with Pythagorean theorem. So I have leg squared, 12 squared, plus leg squared, 16 squared, equals hypotenuse y squared. So that's 144 plus 256 equals y squared. Okay, that gives me 400. And the square root of 400 gives me 20. So y is 20. So think about this for a minute. I want the question mark. Do I know anything about this other piece of this segment? Well, hang on a second. That's a radius. And I know that the radius of the circle is 12. Because the radius is the same no matter what point on the circle you draw it to. So if y is 20 and that piece is 12, how do I get the question mark? So question mark is going to equal 20 minus 12, which is 8. All right, let's look at one more. Uh-oh, this seems to have only told me about one side of the triangle, and it's asking me about another side. Here's my right angle right here. And these are both part of the hypotenuse. And I can add them together to get how long the hypotenuse is. Hypotenuse is 14. But how do I figure out the question mark without knowing the other side? Well, just like before, this is a radius, which means this is also a radius. And every radius of the circle has the same length. So I know that that side is also 8.4. So if I call the question mark x, I've got leg squared plus leg squared, 8.4 squared, equals hypotenuse, which is 14 squared. 8.4 squared is 70.56. 14 squared is 196. Subtract to get x squared by itself. (196 minus 70.56) is 125.44. Take a square root. And that gives you the x is 11.2. Okay. The last type of problem is asking, well, this segment right here, segment AB, it sure looks like that's a tangent segment. It sure looks like if I kept going like this, it would only touch the circle at point A. But is that true? Would it really only touch the circle at point A? Or does it kind of dip into the circle and cross at 2 points if you zoom in enough? Is it really a secant if you zoom in enough? Or does it actually touch the circle just at point A, or does it cross and touch at 2 points? So the question is it really a tangent? Well, the way we need to figure that out is we need to find out, is this a right angle? So in order to figure out whether A is a right angle, we need to figure out, does the Pythagorean theorem work? So the Pythagorean theorem says that if I add leg squared plus leg squared, I should get the same thing as hypotenuse squared. So what I want to find out is if I do 9.9 squared plus 12.6 squared, does that give me the same thing as 16.5 squared? Okay, so 9.9 squared plus 12.6 squared is your a squared plus b squared. 16.5 squared is your c squared. So if it's a right triangle, those should equal the same thing. If they're the same, that means, hey, it's a right triangle. which means that is a tangent segment. So let's find out. 9.9 squared plus 12.6 squared is 256.77. 16.5 squared is 272.25. Well, those aren't the same. That means that a squared plus b squared is not equal to c squared. A squared plus b squared is not equal to c squared. So what it means is angle A isn't a right angle. Which means that segment AB is not tangent to the circle. So in order to find out if something's tangent, you check a squared plus b squared, you check c squared, and you see if they're the same. If they're the same, it's tangent. If they're different, they're not tangent. So let's look at a different one. So I want to know, is this a right angle? Okay, now I have to do a little detective work because they haven't given me all the sides of the triangle. So the radius is 3.2. Here's another radius. Now the whole side of this triangle, 3.6 plus 3.2 is 6.8. Now it doesn't matter which ones are A and B, but this would be little c right there. That's the hypotenuse, if it's a right angle. Okay. So let's go ahead and check. So a squared plus b squared, leg squared plus leg squared. Let's find out what that would be. That would be 46.24. C squared, 6.8 squared. Oh, look, that's 46.24. Those are the same. Okay, and again, just so you can see, this is your a squared plus b squared. This is your c squared. Okay, so what this means is that angle A is a right angle. So segment AB is tangent to the circle.